The objective of this demonstration is to implement RK-2 method, the Rangkatha method of order 2, which claims the accuracy of second order Taylor's method. And we would like to implement it on the problem of radioactive decay, which is governed by dy dt equals minus lambda t, this differential equation. Our steps in RK2 methods are to calculate K1 and then K2 and then yi plus 1, one step at a time. So in Python, I would like to now import the library numpy as np and import matplotlib.pyplot as plt. So I reserve a cell for this. Okay, this is working now. In the next cell, I would like to define my problem, the general differential equation. The first order differential equations are the function of time as independent variable and y, which is the dependent variable. And the same structure prevails for the system of differential equation. In the system of differential equation, this f of ty is going to be t as independent variable, where y is going to take the form of a vector of dependent variables. However, the structure will remain the same. Okay, so how it is defined? So I define, well, I require the indent. So I say that this is dy and it is equal to minus lambda times t value, and I return the value dy, and that's it. So that is the description of first order differential equation in explicit form. Now let's define the problem variables. We have to have our first variable as the constant lambda value. Let's say it is 1, and the initial condition y of 0, it is equal to 100. Let's label that one in the comment that this is the initial condition. So the step size, it is in the control of the analyst. So for this problem, let's consider it to be 0.1. This is the time step. So, okay. So these values are then generated. Okay. Now we have to create the vector of time and vector of y values, right? So I create a vector of time for this step size. So t start, it will be from 0, right? And t end, we can provide any value. So let's consider a value 5.0. So let's generate the time vector t time. So okay, let's just write it t. T is equal to numpy. I prefer writing linear space. Linear space, it says starting value. So t start. Well, there was a great facility provided by the Google Colab. So the function linear space, it is going to create a vector from the starting value to the stopping value and with the number of points. Okay, this is one option. So you can write end value. So for example, it is here t start to t end. So in Python, the last point is eliminated. So since I have defined an h value, So I should better choose the other option, which is a range function. So, okay, this is a nice one. So it says start of the vector, stop of the vector, and the step size. So this would be preferables that we can define with the step size. Okay, so I create the array t start, t end, t end, uh, and with the step size of h, right? This is true. And now with this one, I'm going to create the vector of y at which the computational values are required. So n, how many points are going to be in array? So I write numpy size of t, because similar size is required to create the array of y. So I required now yc as the computational values for y. So it is numpy a range, no, not a range. I fill all the values with zeros. So zeros, shape data type, float. Okay. So I'm looking for n zero values. This is going to be a vector. Okay. N zero values. And well, it should be written in shape. So I write n1, and data type is float. Right. I can instantly test that one, whether this command is fine. So I create an array numpy zeros. If I write 5, and okay, let's compromise for the time being in this checking state. So what it has created? Okay, an array of 5 zeros. So it means this n is sufficient to create the array of n zeros. Okay, fine. So the setup is there, right? Now, this was for testing. Okay. Now we have to write our algorithm. So the initial condition, it is going to be the first element of array. So why not? So this is the setting up the initial condition. So initial condition has been set. Okay. Now, this is very interesting that you can write in terms of the indices. So in terms of I, you can see the algorithm. So I write here for I in range n, there are going to be n points, right? So it will start from the index I will start from 0 to n minus 1, right? So 0 to n minus 1 with this one. With n calculations, I think I must have n minus 1, because initial value is available. Okay. So I start from 0. So the first thing I have to calculate k1. So k1 is equal to h. H is defined. H times f of ti and yi. That's it. I is 0. So the way it was written in the formula, right? The function was defined. Then what is k2? Very interesting. K2 is h times f of t I. So the position of t will be replaced by h by 2. Ti plus h by 2, and y position will be replaced by yi plus k1 by 2. Right? Case has been written. Now yi plus 1 will be equal to the previous value of y plus k2. Okay, this should be computational yc, and this should be yc, and there it must be yc, and this must be yc. And that's it. And that's it. So let's see whether we have performed the calculations correctly. So no error has been returned. So you can notice the tick mark. So the next is the comparison with the analytical solution. So why exact or why analytical? Why analytical? So I can create the array directly. So it is equal to y naught times numpy e raised to the power minus lambda times the value of t. So this will create the ya. Okay, yes. This is a logical and legal operation in Python. Okay, so analytical calculation is correct. Now we have to see the numerical calculation yc. yc. It seems there is something wrong. So we have to check our expression. Okay. So yc, h times f of ti, yc of I, h times ti plus h by 2. This replaces the t and yi plus k1 by 2. k1, and this is yci plus k2. So now we have to check the numerical values. Okay, let's check the values. I'm interested in seeing the creation of array T. So it has been rightfully calculated. And then okay, the other check that was suggested by students, which was quite obvious, it is to write the function. So when I write the function, it seems there is something wrong, that f of 0 y should be 100. So let's correct the function. Oh, and here it is. The function definition is not consistent with the definition. Oh, and the error was generated because it was written wrong in the first step. The radioactive decay equation is not dy dt equal to minus lambda t. It is minus lambda y. So the error was from the beginning. So let's correct it. So it's y, and I have to activate it. And then if I test the value from the function, so now it is fine, but there is minus 100. Yes, minus 100 is fine. The first value is with minus lambda y. Okay. And then we have to activate the numerical calculation part. So numerical calculation part has been now completed. And if we now see the values of yc, so they are now reasonable. And we can see its pictorial depiction. So I generate a plot of t and the exact value as ya, and I will plot it with red. Sorry. Okay. With red circles, and T and Y computational is plotted with blue dots, and PLT X label. It is the time domain, and PLT Y label. It is the activity. And since we are plotting two curves, there must be the legends. So legend, the first one is analytical. And the second one is the values from RK-2. Okay. So the numerical result has hit in those boxes, the analytical boxes. Amazing, isn't it? Yes, this is indeed amazing that the analytical result is with the red, red circles, and the RK-2 has rightfully hit on target. That's amazing. And now, if you want to see the sensitivity, so you can see the step size, right? So 0.2, let's consider, say, 0.5, a bit larger one. Well, we have to activate the cells. Now there must be the recreation of arrays, and then there is again the computational algorithm. This is the implementation of the algorithm. So computational part. This needs to be reevaluated. Yes. And this needs to be reevaluated. And let's see that one from the plot. Okay. So as the step size is going to increase, the errors are going to grow, right? So this was a vivid demonstration of the RK-2 method. On similar lines, the higher order methods and RK methods, the class of RK methods, they can be implemented. So with this success, let's stop at this point.